Hello, so welcome to the Newtonian Mechanics series of AS level physics. Today we'll be starting with the chapter of kinematics in the Newtonian Mechanics section. So, what is kinematics? Well, kinematics is really a branch or it is developed in what is called the classical mechanics. And kinematics is a part of this classical mechanics where you deal with a motion of any points. So it deals with motion of points and any system or bodies. You could say a group of points as well. So you could have a group of objects. But the main thing is that it does not touch, so without touching or without considering the effect of forces on these points or objects, right? So we'll ignore forces in studying kinematics, which means that if you have an object and the object is moving, then you're only concerned with this part, which is the motion of this object. You are not concerned what caused this object to move. So there must have been a force that caused this motion, but you are not concerned with this one as long as we are talking in kinematics. So let's start by defining some of the quantities that we'll be often using in kinematics. And so the first one is really distance. So how do you define distance? Now think of the same example. Consider you have a box and it moves in space. So it will move some value from, suppose this is point A to point B, and you have to define what this movement is, and you use the concept of distance. So it's really the number that my object moves from point A to point B. Note that we talked in terms of a number and we are not concerned with in what direction is the box moving. Which leads us to the next thing, which is known as the displacement, where displacement is actually concerned with the direction of motion. So displacement, you can have the same definition as distance, but with an additional term that describes the direction. So you can say that it is the direction, or sorry, it is the distance, really, it is the distance any object covers, right, from a fixed point, and this fixed point will be really a fixed reference point in a particular direction. So what's happening really is that, consider you have this object again and it moves. Now it can move either in this way, or it can move either in this way, or of course it can move in multiple other directions as well, but let's talk about these two. So now if you say that it moves a certain number in this direction, then you can assign a signature to this number. Suppose you're signing plus or positive of that number, then you're assigning this signature to this direction of motion. And then the opposite of this signature would be negative and this particular number. Now negative is implying that the direction is in this way. Now this method of signatures is really completely dependent on you. I could have really defined this thing as positive and this thing as negative. But once I pick a particular signature, I have to stick with that. So you could have also then use this as positive and this as negative. And now if I choose this, then I must stick with this thing during my entire calculation. Hence, I say that displacement really is a vector quantity. Now, vector quantities, I'm sure that you know of them. They are concerned with the number, which is the magnitude of the vector or the strength of a vector, and the direction is also included when you're defining a vector quantity. So displacement is our vector quantity. Now that we have defined distance as well, let's define something that is called speed. So speed is really related to distance. It is actually directly related to distance, and it is just the distance that my object will cover in said time, right? So it is the distance that is traveled by an object in some time, right? So you can say it is distance that the object covers per unit time, right? So that means that speed is, because distance is a scalar, it's just a number, right? It's just a number, which implies the scalar nature. So speed is also just a number which is scalar. It is not concerned with in what direction is my object covering this distance per unit time. But then, because I have defined displacement, I can define a quantity that is known as velocity, and velocity is simply defined as the time rate of change in displacement. So how is my displacement changing? How fast is the displacement changing? That's the velocity. And now velocity is a vector quantity because displacement is a vector quantity. Note that displacement is not, or velocity, because it's related to displacement, it does not really mean the total distance traveled, because now let me try to visualize this thing for you. Suppose that you have this point, let's call it point A, and you have a point B over here. I can reach from point A. If I start my journey at this point, I can reach to point B if I draw a straight line from A to B. Now this straight line is the displacement. This is the shortest path in reaching from point A to point B, distance wise, displacement. Now you could have also done this thing. You could have taken this route and come to this point, let's call it some point P, and then you could have reached point to point B. Now this thing, let me use a different color for this. So let's draw this with this blue. Now, so you can see that in this case, if I had taken from point A to point P and then point P to point B, then I would have still reached towards my point B, but the distance that I'm taking is more compared to if I had taken this path from A to B. So the distance, which is AP to PB, is greater than the distance from A to B directly. And this thing, the shortest path between these 2 points, which is this line AB, is known as the displacement. So with this now, having velocity, understanding velocity, we can define what is known as the acceleration. Now, acceleration is simply the time rate of change in velocity. So how fast does the velocity of an object changes is known as acceleration. Now, acceleration is also a vector quantity. Now, if I have an object that is moving in this direction, so this is the velocity of this object, and let's suppose that the acceleration in this object is in the direction of this velocity, which means the vector would still be pointing like this. So this is the acceleration vector. In that case, this velocity starts increasing, right? So this is the case of increase velocity. However, suppose that I have the same thing and the object moves in this direction, but the acceleration is pointing in this direction, which is exactly 180-degree opposite to the velocity vector, or you can say it is anti-parallel to the velocity vector. So in this case, this acceleration is working to decrease the velocity of the object, right? So this acceleration, if it points in this way, you can say that what's happening is that the acceleration is causing the change in velocity in the opposite direction, which means that the velocity, instead of the number increasing, it would start to decrease. You could have another example as well, where the direction of motion changes. And that is, suppose that I have this object and the velocity vector points in this way, so which means that it's just moving in this direction, and the acceleration vector is perpendicular to this vector v. So let's suppose, for the sake of example, let's draw it in this way. So this is the acceleration vector. What would happen in this case? Well, the velocity will not be affected because the acceleration vector is independent of this direction. So it is completely orthogonal to the velocity vector, which means that the magnitude of the velocity is not going to be affected at all. However, the acceleration, because it's pointing in this direction, it's trying to change the velocity, but in this way. So it's pointing orthogonal to this motion. The resultant of this would be that we have this acceleration over here. The resultant would be that it would change the direction of this object. So instead of now moving completely in this way, the acceleration vector is pulling it to some center. So what happens is that the direction of the object, direction of motion, starts to change, and maybe it might change in this way. It will start moving in this direction. Now we can assign mathematical expressions to velocity and acceleration. So mathematically, the velocity is expressed as v, which is a vector, so we add this vector arrow like symbol on top of it. It is the change in displacement, so delta s, where s represents the change in displacement, delta s, divided by the time it takes to change that displacement. So that's delta t. So that's how you can define a velocity vector mathematically. Similarly, acceleration is the time rate of change of velocity. So mathematically, you can also write an expression for acceleration where a vector is the acceleration, and that is simply equal to the change in velocity vector divided by the time that it takes to change this velocity, delta t. So if displacement is measured in meters and time is measured in seconds, then velocity is measured in meters per second. So if velocity is measured in meters per second, then acceleration is measured in meters per second divided by seconds, which is just meters per second squared. So now let's try to understand the difference between velocity and speed. We'll do that by considering that you suppose that you have a train. Suppose you have a train that moves in this circular path, right? So it starts its journey at this point A and it completes its journey in this way and comes back to point A. So that's really the definition of a circle. Now let's suppose that the circumference of this circle is 2.4 meters. Now the train starts at this point A and you take a stopwatch and you start timing this motion of the train. Suppose that it covers this distance of 2.4 meters, so it goes around the circle one time completely in 4.8 seconds. So you have timed it to be 4.8 seconds. Now you want to find the speed or the average speed of the train. And then I say that let's find the velocity of this train as well. So let's first start by finding the average speed of the train. So we know that average speed or speed is defined as the change in distance divided by change in time, which means that because the circumference of this circle is 2.4 meters, which means that this length is really 2.4 meters. So if my train starts from point A and it moves on this line, so if it covers this whole complete round and comes back to point A, it has traveled a distance of 2.4 meters. So in place of this distance, I'll just put 2.4 meters divided by, we have time. Now the time that we measured using the stopwatch when it started its journey from point A and first time reached point A back, it took 4.8 seconds to do so. So the change for time is 4.8 seconds. Now, if I do the math right, then this gives me 0.5 meters per second. Now, this is the average speed of this train that moves on this circular track as so. Now, suppose I also want to compute the velocity or the average velocity of this train. Remember, average velocity is defined as the change in displacement divided by change in time. So how long did it take to cause this displacement? Now, S is displacement, right? So if you look at this figure, you see that if I start my journey at point A and I come back in this round to this point A, that's one lap. And the displacement for this one lap is 0 because I started at this point A, and whatever path that I take, it doesn't matter if I'm coming back to this point A again, then at this point my displacement is 0. I have not really displaced at all, even though we have covered all of this distance, but the displacement by definition is 0. Which means similarly in this case where we have this track, the displacement vector will be 0, and hence this is just 0 divided by delta t, which doesn't matter because this will give you 0 meters per second. So the average velocity is 0. Now, just a point to note over here is that it's always a good idea to have the units like this included even while you're working in your calculations, because this can help you to avoid any mistakes of units in your calculations. So, and this thing also helps you to keep your equation balanced at all times. So by doing this problem, we really understood the difference between speed and velocity. Now let's consider something else where we'll try to understand acceleration as well. So for example, consider that I have a car, and you'll have to ignore my drawing, but this is a car and it travels, suppose in this direction, and it travels on a straight track. So it travels on this straight track, and suppose that where it starts its journey, it starts from some reference point 0 and it covers this track which is of 840 meters, and the car is moving at a speed which is constant of 35 meters per second, which means that every second it will cover a distance of 35 meters. Now, at a particular point, the driver is going to apply the brakes in the car. And when you apply brakes, imagine what happens. The speed starts to slow down, which means that the car will start to de-accelerate, or you call it decelerate, which means the opposite of acceleration or a negative acceleration. And he applies the brakes until the car comes to a stop. Now, the brakes were applied and the car came to a stop at a constant rate in 7 seconds after the brakes were applied. Now, before the brakes were applied, let's try to understand how long was the car traveling at this constant speed of 35 meters per second. So time for which car moves at constant speed, which is given to us as 35 meters per second. So we know that the velocity is given, and we know that 840 meters it's going to cover at this constant speed. And then at this point, the car applies brakes. So it's going to cover a distance of 840 meters. So the displacement that it covers is 840 meters, while it's moving with the velocity of 35 meters per second. And I'm required to find this time for which it is moving at this speed. So I have these quantities, and I know an equation which relates all these three as V is equal to delta S by delta T. Now it's just a matter of rearranging this expression for delta T. So that is delta T is equal to delta S by V. So if I just put the values in this, as delta S is 840 meters divided by velocity, which is 35 meters per second. So meters and meters goes, and this second will come upstairs, and this gives me delta T by doing the math as 24 seconds. So it takes 24 seconds for the car to remain at this constant speed. So the car was really moving at this constant speed of 35 meters per second up until this point for 24 seconds. Now, let's try to understand the acceleration of my car when brakes were applied. So when I braked, what is the acceleration of the car at that particular time? So we are given the velocity, right? So at first it is moving with 35 meters per second. Now, at some later time, this velocity becomes 0 meters per second, right? Because the car is going to come to a stop, and so it will be covering 0 meters in every second because it's not moving, right? So the change in velocity is 0 meters per second, which is the later velocity, minus 35 meters per second, which is minus 35 meters per second. So that's the change in velocity. Now I have delta V as 35 meters per second, and I have delta T, which was 7 seconds after the brakes were applied. It took 7 seconds for the car to attain this velocity of 0 meters per second, or you can say it took 7 seconds for the car to go from 35 meters per second to 0 meters per second, which is at rest. So delta T is 7 seconds. I am required to compute the acceleration. By the way, delta V is minus 35 meters per second. Minus sign is telling you because V is velocity, so it is now moving in the opposite direction, right? So this means that I want to calculate the acceleration. The equation that relates all of these is acceleration is delta V by delta T. So delta V is minus 35 meters per second, while delta T, which is 7 seconds. So this becomes, if I do the math, minus 5.0 meters per second, so that's meters per second squared. So here we see that the acceleration is minus 5.0 meters per second squared. This minus sign is really telling you that the velocity is decreasing in this problem, which is what we expect because the brakes were applied at this point, and the brakes are applied to decrease the velocity of the car.